Another piece of information before getting into the calculus part. I mean, it's well, we already reviewed a little bit of aspects from algebra, some definitions, some geometric aspects that we will require for later when we start constructing the definitions of a limit, the definition of the derivative based on the definition of limit, and the like. But this course heavily relies on using our trigonometry, and well, I mean, in 50 minutes we're not going to go through the entire trigonometry course because, well, actually many of the aspects we will be reviewing along the way as it shows up on the calculus exercise and the calculus aspects. But one that I would like to quickly review is knowing how to evaluate trigonometric functions, in particular for the most common angles, the ones that we can find on the unit circle. Okay, so well, there's a couple of ways to compute trigonometric functions. Number one is the unit circle. If you have it memorized already, you feel comfortable with it, that's fine. Just use the unit circle. A good way to memorize all these values, well, my advice is to only memorize the ones that are on the first quadrant, and check this pattern. So notice as we go counterclockwise with increasing angles, see how the y values get bigger? 1, 2, and 3. And in this case, the x values get smaller every time. 3, 2, 1. So basically there's an invisible square root of 1 over 2, but I mean, what's the square root of 1? Is it just 1? And basically there would be a square root of 0 over 2. Well, that's all 0 as well. Alright? And then knowing this pattern, knowing this 1, 2, 3 points, you can use that same information to fill in the rest of the points. I mean, because this point will have an specular image over here on the second quadrant. It's the same point, but the one that changes sign, it's only the x value. And same here, same point, x changes sign. What about, for example, for the fourth quadrant? This point right here, it's the same as that point right there, but the one that changes is the sign of the y coordinate to negative, and same for and the same is true for the other points. So that's a good pattern to memorize the unit circle in case you haven't memorized. Okay, so let's put in practice some of these calculations, and of course, so let's look at basic identities that are important to keep in mind if you are using the unit circle, because recall that the points along the unit circle are of the form cosine and sine. Alright, so that's those values are only for cosine and sine, and of course you might be in the need of finding trigonometric functions for tangent, secant, cosecant, etc., and those are not in the unit circle. And for this reason, it's important to know or to take into consideration only these basic identities. I mean, there's more identities such as the the double angle, Pythagorean identity, but we're not going to use those to compute values of trigonometric functions. So all we need is this to find cosecant, which is the reciprocal of sine, secant, which is the reciprocal of cosine, tangent, which is the quotient between sine and cosine, and cotangent, which is the reverse, the reciprocal quotient. That's all we need. So let's have a look at some examples. Find the exact value of each function. Sine of 135 degrees. Okay, so let's go to the unit circle and locate the 135 degree angle, which is right here. Well, because in this case we want sine, which value is it going to be? The x value or the y value? The y, which in this case is square root of 2 over 2. All right? Just that. cosine of 5 pi over 4. Okay, let's locate the angle 5 pi over 4. So 5 pi over 4 is right here. So in this case, they're asking us for cosine. Is it the x value or the y value? X. So that's a negative root of 2 over 2. Okay, careful when you have negative angles. So there's a couple of ways. You might want to use either the even and odd properties to rewrite this, or just count the angle in the negative direction. So instead of going counterclockwise and find the 2 pi over 3, we would be going clockwise for the negative direction for angles along the unit circle. And so for example, if we were looking for 2 pi over 3, well, clockwise 2 pi over 3 is here, alright? However, no, we don't want that angle. We want the angle in the opposite direction. That is, it's going to be the equivalent of 4 pi over 3. Are you guys following me here? Yep. Okay, so they're asking us for which function is it? Tangent. Oh, here is where we're going to need the trigonometric function. That is, okay, let me rewrite this as a quotient between sine of negative 2 pi over 3 over cosine negative 2 pi over 3. Alright, well, sine of 2 pi over negative 2 pi over 3, which is the same as the 5 pi over 3. Okay, so sine, which is negative root of 3, and cosine, which is negative 1/2. So let's just write that quotient, negative root of 3 over 2 over negative 1/2. And well, from here, check how we can divide out these twos, and ultimately negative over negative is positive. Root of 3 over 1, that's simply root of 3. Okay? Does that ring a bell from pre-calculus, from math analysis, whatever class you took? Where you learned the trigonometry, integrated math maybe? Alright, secant 60 of negative 60 degrees. Okay, let's count 60 degrees first of all. So 60 degrees positive would be this pi over 3, but that's in the positive direction. We want the negative one, so we can go from 0 negative 60 degrees, and that's 5 pi over 3. But because we want, in this case, what they're asking for, secant, how about we rewrite secant as 1 over cosine? And the reason to that is that, again, the unit circle gives us values of sines and cosines. So whenever we are in the need of evaluating other functions other than sine and cosine, we need to use these basic identities to write these functions in terms of sines and cosines. And well, cosine of negative 60 degrees. So negative 60 degrees is this point right here. Cosine, is it the x coordinate or the y coordinate again? X, so that'll be 1/2, right? So this will be 1 over 1/2, but what happens when we divide by a fraction? Multiply by the reciprocal, final answer, 2. Okay? Cosecant 7 pi over 4 first. Well, we don't have cosecant on the unit circle, only sines and cosines. Well, so let's write cosecant in terms of either sine or cosine. Well, in particular, we know that cosecant is the same as saying 1 over sine. And let's locate sine of 7 pi over 4. Let's go to the unit circle. What was that again? Oh, 7 pi over 4. And it's positive, so 7 pi over 4 right here. We have root of 2 and negative root of 2 because we're looking for cosecant, which is 1 over sine. Is it going to be the x value or the y value? The y value, right? So the one with the negative sign, 1 over negative root of 2 over 2, which is negative 2 over root of 2. And typically when we get these results, we rationalize denominators. Typically we don't want these denominators with radicals, and this will be negative 2 root of 2 over 2, which reduces to negative root of 2. Alright? Again, basic calculations, but in some cases, again, we need these identities to go beyond sine and cosine. Now we have cotangent, that's cosine over sine. Cosine 240 degrees over sine 240 degrees, and well, the usual. Let's go back to the unit circle. Look for 240 degrees is the same for pi over 3. And well, in this case, we're looking for cotangent. Cotangent is the reciprocal of tangent, right? In this case is cosine over sine. That's the x over the y. So that's negative 1/2 over negative root of 3 over 2. Cancel these two. Negative over negative is positive 1 over root of 3. And be sure to rationalize denominators, leaving us with a square root of 3 over 3. Alright? But again, it's important to know the unit circle and know its values, find a pattern to memorize at least the first quadrant. Then you get specular images of those points by changing the corresponding signs into the corresponding quadrant. Alright? So instead of having to memorize every single value, sign, and the like. So there is another way to evaluate trigonometric functions instead of memorizing the unit circle, and this is actually my preferred way, by memorizing the special triangles, the 45 degree, the 60 degree, and the 30 degree angle. So whenever we have a 45 degree angle, the lengths of the sides are 1, and the hypotenuse has a length of a square root of 2. We can verify this using the Pythagorean theorem. And the same for the 30 and the 60 degree triangle. They're actually the same, they're just flipped. So the thing is, when we have a 60 degree angle, that's a large angle. That means the base is small, it's a 1, and the height is root of 3. On the 30 degree angle, smaller angle, larger base, smaller height. And well, depending on which quadrant are we at, well, we need a reference angle for the corresponding the corresponding quadrant. Okay, so let's do sine of 135 degrees. Okay. So it's important to know that as well, if you go this way, to see how to find out what multiples, whether the given angles are multiples of what angles. Are they multiples of 45 degrees? Are they multiples of 60 degrees? Are they multiples of 30 degrees? And from there to choose the correct triangle. So for example, 135 degrees. Isn't that a multiple of 45 degrees? If we go to the unit circle, for example, 135 degrees, it's going to give us the 1, 1, root of 2 triangle in this case. So this is what we're going to do. And I made a silly mistake. I'm going to fix it in a second. So, yeah. Okay, Cartesian plane first. And that's the 45 degree angle. However, yes, the regular 45 degree angle in the first quadrant has dimensions 1, 1, root of 2, but because of the orientation here, this will be negative 1, 1, and root of 2. And from here, we're going to use the SOHCAHTOA definitions of the trigonometric functions to compute the trigonometric functions. In this case, sine. What's the definition of sine in terms of SOHCAHTOA? Opposite over, so the opposite, which is 1, and the hypotenuse, which is root of 2, and actually rationalizing, we get square root of 2 over 2. Isn't it the same result as we did using the unit circle? So whether to choose the unit circle or the special triangles, either way you should get the same result. So ultimately I'm presenting this just so you choose whatever you feel more comfortable with when it comes to computing these trigonometric functions. Cosine of 5 pi over 4. What's that? Well, 5 pi over 4, it's located on the third quadrant. Oh, again, that's going to be another 1 root of 2 triangle, the 45-degree triangle. All right, so but in this case, careful, because this is -1 because of the direction and with the direction on the quadrant, and the hypotenuse is always positive. Okay, that's the thing here. The hypotenuse is always positive. So from here, cosine by definition, by the SOHCAHTOA definition, what's that? Adjacent over hypotenuse. The adjacent is -1. The hypotenuse is root of 2. And rationalizing denominator, that's a negative root of 2 over 2, which is the same result that we got using the what's it called? The unit circle, isn't it? Which one do you prefer? Do you prefer triangles? Do you prefer the unit circle? Did you learn both ways in high school or in your previous class? All right. Okay, let me do one more and actually change to the next topic, which is review of basic functions. So let me just do one more. The last three, I will just skip them. I'll leave you with those as an exercise to verify those results using whether well, in this case, the triangles, right? So tangent of -2 pi over 3. So -2 pi over 3 is, so 2 pi over 3 would be here. -2 pi over 3, if we go in this direction, would be this one right there. So that's going to be the triangle that is the -1 root of 3, negative root of 3, and 2. So let's construct that triangle here in our exercise, okay? -1, negative root of 3, and 2. And well, we're asked to compute the tangent function. So what's tangent for that triangle? Isn't that opposite over adjacent? Negative root of 3 over -1, that's root of 3. Isn't it the same result as using the unit circle? Yes? Is it? Okay. So let's move on to another topic. Where's the document? Okay, functions and models. And okay, so another very important aspect that we need in calculus, it's the notion of what a function is. And well, actually, before going through what a function is, there's two concepts that are tied together. Number one is a relation, and the other one is a function. So the thing is, the relation is only a correspondence between two sets. You know, when we assign certain values from the domain to elements in the range, right? That's all we do, and we can write these relations as bubbles with a list of numbers, or pointing with arrows, or as order pairs. And then from here we define the concept of a function. In some cases, those relations may define a function, but some of those may not define a function. So a function is actually a special kind of relation that associates every single element in the X, in the domain, with only one element in Y. For example, you know, the thing is that every single input has exactly one output. That's what a function is, you know. And well, there's a few ways to represent functions. Actually, 4 ways. Verbally, you know, when we when we're doing science, for example, and we are observing certain phenomena, like, for example, in chemistry, and the gases law, for example, let me write it down. So, PV over T, for example. In this case, well, the pressure of a gas, or rather the amount of gas. Let me call the amount of gas. And well, it's directly proportional to the pressure and the volume, but inversely related to the temperature, right? So that's, in a way, that's what we observe, and that's what we interpret in words. So that's one way to interpret this verbally. Numerically, well, when we are making measurements in the lab, right? And we write a table of values. All right, that's another example of a function in terms of numerically, table of values. Visually, very commonly by a graph, and algebraically when we have an explicit expression, you know, like f of x equals x squared plus 5, f of x equals e to the 5x minus 7, well, you name it, right? Infinitely many ways to describe this, of course. Now, a classical picture of how do we describe a function? Well, in the graphic point of view, we have the graph of some f of x. So the domain of the function, it's also known as the input, and the range of the function is the output. And for example, you might have seen this picture before. The machine function. Have you seen it before? So, for example, f of x, you know, for example, when you have a coffee machine, you know, so what is the domain of the coffee machine? What's the okay input for a coffee machine? What do you put into? As an example, okay.
You put milk in, right?
What is it?
Then you put milk in, right?
Yes, so water in a coffee machine, water, coffee, maybe you put some cinnamon in it or to get some flavor, you know, and then the output will be the coffee. So can you input a baseball in it? What's going to happen? It's going to blow up, right? So that's another situation with some functions that blow up at some inputs in particular. For example, what about f of x equals 1 over x? You can plug in your favorite number to this function except which value? We cannot plug in equal to 0 because it goes undefined. In the same way like the coffee machine, the okay inputs, water, the coffee, ground coffee, cinnamon if you want some flavor, etc. But a baseball, it's not part of the domain, right? So those are the limitations for certain kind of functions and the analogies. So input and output. Very classical picture to describe what a function is. Well, so we can evaluate functions from graphs or from explicit functions. And to evaluate from explicit functions, all we do is plug in for whatever reason the letter x, and simplify. But for graphs, okay, f of 1 and f of 5. And then what is the domain? Okay, what is the domain and the range of this graph? So let's observe this graph, and well, let's assume in this case, for the sake of simplicity, the scalings of these lines go by 1. All right, f of 1. That means what is the output when the input is 1? So if the input is 1, what's my output? 3. F of 1 equals to 3. And f of 5, that is what is our output when our input is 5. Well, let's count them. That's 1, 2, 3, 4, 5. And our output looks like, it's not even 1, looks like 3/2 maybe. Yeah. Is it? 1, 2, 3, 4, 5. Yes. Yeah, it looks like 3/2 sort of. Negative actually, right? Negative. Yes. Uh-huh. 3/4? 2/3? Oh, not 3/2. That's what I meant. Negative 2/3. Yes. You guys are right. Yep. Domain and range, and we need to be careful when they ask for the domain and the range by a graph, because, well, the graph must have certain features to take certain approach. Okay, so what would be the domain of this f of x here, of this graph?
Y. F of x will be y, right?
Yeah, f of x will be the y, the range, but the domain are the OK input, which is the x's. In this case, well, to find the domain of a function given the graph, we kind of scan the graph from left to right. What's the smallest value of x and what's the largest value of x? Visual, what is it?
0,7.
0,7. 5, 6, yes, 0 to 7. Do we agree with 0 to 7?
Yeah.
What about range?
-2.
-2 to 4. Good. All right. Now be careful. This, in some cases, is misleading, but this little bit of information will change the whole game. What if you had this otherwise?
It'd be 0 to
0 to infinity. So the domain would be 0 to infinity and parentheses for infinity. And what about the range? -2 to infinity as well, right? Good. So, and well, how are you going to see this different? Well, in this case, notice the original graph doesn't have any arrows at the endpoints, but well, when I just made this up to change the game, so that's how it's going to work. Okay, so to determine whether a function, a given graph represents a function or not, we have the vertical line test, right? And if the line crosses only once at every single point, well, then that defines a function. But otherwise, if you have a vertical line crossing the graph of the function at more than one point, then it is not a function. So the question is, function or not a function?
Function. Not a function.
Nope.
No.
And no. All right. So no, function not a function. Okay. Think of this. The way I like to explain this is like, can we be in two different places at the same time? Can we be in class and at the beach at the same time? No. We wish, but it's not possible, right? So that's why this is not a function in this case. Okay. Another piece of information is piecewise functions. You know, well, in this case we need to take into consideration the parent function. You know, x squared, the opening up parabola, the diagonal line. What else? The cubic, the V-shaped one, which is the absolute value of x. What else? The exponential, the logarithm, and then also understand what these conditions mean. So, for example, they're asking us to graph this piecewise function 1 minus x, which is in this case is a linear function with a negative slope, and then we have x squared, which is an opening up parabola, the very parent parabola graph, right? Well, if we were to graph this without these conditions, then we would have doing, whoops, now let me do this well, 0, 1, and 4, all right? And the line which is 1 minus x, which would be these lines together, the two together, overlapping and intersecting, right? However, that's not the case. In this case, we have conditions. And typically, a table works, you know, or if you can do well, in this case for the linear equation, let's do the rise over run, and let me do some of the points. So the y-intercept, which is 1, and the rise over the run, that's 1 and -1, 1 and -1. All right, this would be the equation of the line, right? However, well, we don't want the whole graph of the linear function. We only want that portion of the graph where x equals where x is less than or equal to -1. So we don't want this part right here, right? So we only want that part of the graph. Are you guys following me here? And be very careful here with the notation on the graph, because notice the condition says x less than or equal -1. That means we are going to have a solid bubble in here. For the parabola, for example, all right, let's do 0 squared, that's a 0, 1 squared is 1, 2 squared is 4, and how about -1 squared, even though it's excluded? But the fact that it's excluded means a lot in here. So -1 squared is +1. However, we are going to have an open bubble in here. All right, that's what it means to have the x greater than or equal. I mean the x greater only. Now, question here, conceptual question: what if we had both the less than or equal and the greater than or equal here?
Then it wouldn't be a function.
Why wouldn't it be a function?
Because then there's two solid points.
Alright, we would have two solid points, so we would be in class and at the beach at the same time, right? So which is not. Alright? So of course, I mean, you can have many combinations of piecewise functions and all that. So let's see what's next. To determine whether a function is even or odd. And I believe we already talked about this, if I'm not mistaken, maybe or maybe not. Well, so a function is even if for every x in the domain, the number -x is also in the domain, and analytically or algebraically, when we evaluate the function at -x, we get back to the original function without changing sign. Right? And otherwise, for the odd functions, when we evaluate the function at negative values, if our output is the opposite of the function, then that's an odd function. And well, I believe we discussed how even functions are symmetric about the y-axis, and an odd function is symmetric about the origin. So for the symmetry about the origin, guys, think of rotating the graph 360 degrees. And if you obtain again the original graph, then there you go. That's an odd function. And well, for the even function, just rotate it about the y-axis, you get the same graph, that's even. Or another way is to you can think of the y-axis as a mirror reflecting the same graph on both sides. That's another way to identify even functions. And well, algebraically, let's determine whether each of the given functions is even, odd, or neither. So to begin with, f of -x, that means whenever we see the letter x, we change with, we replace with -x to the 5th. Alright? Now, what do we get when we raise -x to the 5th power? Negative, because it's an odd power. Negative quantities raised to odd powers become, or rather remain negative. So that means this is equal to -x to the 5th plus -x, which is -x. But now let's see. Let's factor out this negative sign. -x to the 5th plus x. Alright, but what is x to the 5th plus x? Isn't it the original f of x? But with a negative sign in front of it? That is, we got the following. We got that f of -x equals -f of x. What does that mean then? Even, odd, or neither? Odd, right? Okay, let's do the next example. G of x equals 1 minus x to the 4th power. We do the same. G evaluated at negative x. That means we will replace every instance of x with negative x quantity. So negative x to the 4th power, what is that going to become? Becomes positive, but because of the negative outside remains negative, so that's g of negative x equal to 1 minus x to the 4. But in this case, isn't this the same original function f of x? G of x? What does that mean? Even or odd? Even. Okay? Even. And last but not least, okay, we have another f of x. Maybe I should call this instead h of x to make, there's a reason why I'm changing the label of this function. It's let's call it h of x. Okay, so we have 2x minus x squared. I'm going to do h of negative x equals 2 times negative x minus negative x quantity squared. So let's do one term at a time. Okay, so the 2 times negative x, that's going to become negative 2x. And this negative x squared becomes positive, but times the negative in front of it becomes negative. Okay, now let's compare. Did we get back the original function?
No.
Is that function the opposite in sign of the original function? No. So in this case, neither.
Wait, why are you putting in the examples like the negative x bars at the start?
So in order to determine whether it's even or odd, we replace x with negative x, and if in a way we output the original, the same function, we obtain an even function. But otherwise, if we obtain the opposite in sign, that's the odd one. Question? Any question?
Is odd symmetrical around the origin?
Exactly. Odd, symmetric about, yeah, I didn't label that. Thank you for asking that. So that's this is the representation of an odd function, a function whose graph is symmetric about the origin, and this is the even one, the one that it's reflected about the y-axis. Question?
What is neither look like?
Well, we'll see in a second. So for the next part of this exercise, so I have 3 graphs right here below these 3 exercises. Can you tell by the properties and by the looks of the graphs which one corresponds to each function?
Yes.
Okay, what about f of x? The first one, x to the 5th plus 4. Which of the 3 might seem to be?
The one in the middle?
The one in the middle. Do we all agree with the one in the middle?
Yes.
And so if you observe the graph in the middle, this is the graph that is symmetric about the origin. So that's f of x. Alright, what about the second one, letter B? We got an even function. Graphically, how would it look like?
The one on the right.
Which one?
The one on the right.
The one on the very right, the third one?
Yes.
Well, and also, notice the sign of the leading coefficient is negative. That means it's going to have something upside down, and that pretty much is an even function. And well, one remaining, there's no...
But you can also tell by the way the graph looks.
Mm-hmm.
Just look at that.
Yes, that's another way. And I mean, look at this function that it's neither. So this graph, well, it's symmetric. Yes, careful. It's symmetric about the line x equals 1, but we're not looking at symmetry about x equals 1. We're looking at symmetry about the y-axis and symmetry about the origin only. Okay? And the last piece of information that I would like to refresh on from pre-calculus, well, to identify increasing and decreasing functions. Well, I mean, I think this is pretty straightforward by just observing a graph because the way we analyze graphs are always from left to right, and then from there we determine that increasing or the decrease or increase or decrease. And well, for this example, with symbols, and we can. Well, we're gonna be looking at this later in the semester when we look at some of the applications of the derivative to determine whether a function increases, decreases, and based on that information, we will determine whether we will have a maximum or a minimum that later we will use to solve problems in engineering and science and economics and business analysis to find values of x prices, for example, to maximize your profit and to maximize a bunch of things. Or when you're constructing like a pen, for example, for your pets, for example, you have an amount of fence. Well, you want to make sure that you have the largest area so your pets have the largest space. Well, we are going to construct a function. We will do some calculus. We will analyze whether it's increasing, decreasing, and find the maximum point based on that information. And well, for now, in the simplest case, we're going to have this graph, and we will find the intervals in which the function is increasing. If you want to put numbers, okay, why not? Let's say A equals to 1, B equals to 7, and how about D equals to 10? How about C equals to 8? And yes, how about that? Okay, just to make you have a more solid example in terms of numbers. Well, so we are going to look at intervals in which the function is going up. So from where to where is going up?
From point A to B.
Which in this case would be 1 to 7. 1 to 7, close parentheses, and then union symbol increases again from C to D, which correspond to 8 to 10. And decreasing,
7 to 8.
yep, yes, 7 to 8. And no, that's all we have for the graph, right? So there's nothing else. So of course we're going to look at this a lot in depth, the theorems and the definitions and all that. You'll see later. Alright guys, so this is what I have for today. Next time we're going to look at, I think, more functions or limits. If you have any questions, I'll be here for a couple of minutes. Otherwise, have a great weekend. See you on Monday.
So are there any assignments due this weekend or no?